The 7 series and Zinc 7000 family include an XADC, which can monitor internal voltage rails and die temperature. Additionally, the XADC can measure external analog signals with a sampling rate of up to 1 meg sample per second, making it a valuable tool for simple signal processing applications. Block diagram of Vivado design. The XADC generates a stream of sample data, which needs to be transferred to DDR memory for visualization or processing. To achieve this, we can use AXI DMA. However, AXI DMA requires the TLAS signal to indicate the end of a packet. To provide this signal, we can use an AXI stream converter between the XADC and AXI DMA. Both XADC and AXI DMA are controlled with ARM core over AXI light connection. Clocking Wizard provides 104 MHz clock, required to run the XADC IP block. Vivado design. Start a new Vivado project targeting the PYNQ Z2 board. Create a block design for your system. Add the Zinc processing system IP block. Run block automation to initialize it with default settings based on the selected evaluation board. Add the XADC Wizard IP block. In the Basic tab, set timing mode to continuous mode. Change the declock frequency to 104 MHz to enable a sampling rate of 1 megasamples per second. Enable the AXI stream interface in the XADC to allow data streaming to DDR memory. In the ADC tab, enable external multiplexer. Select VPVN from the drop-down list. It allows us to capture the analog signal from this differential pins. In the Alarms tab, deselect all alarm options to simplify the design. In the Single Channel tab, ensure the VPVN channel is enabled. Make the VPVN input as external. You will assign these differential pins manually after synthesis. Add a Clocking Wizard IP block to generate a 104 MHz clock. In the Output Clocks tab, configure the first output clock to 104 MHz. Connect its input to the PSBL clock from the Zinc processing system. Add an AXI DMA IP block to handle data transfer. Disable Scatter-Gather mode and Read channel. Set the AXI stream data width to 16 bits to match the XADC output. And finally, enable Allow Unaligned Transfer. We need to generate TLAS signal using AXI stream subset converter. Enable TLAS on the master port. Configure it to generate TLAS after 256 samples, allowing the AXI DMA to transfer 256 sample chunks to DDR memory. Now we can connect the AXI stream output from the XADC to the stream subset converter, and then to the AXI DMA. Connect all IP clocks to the 104 MHz output from the Clocking Wizard. At this point, we can let Vivado's auto connection feature to complete remaining connections, such as AXI light interfaces and resets. Let's have a quick review of the design. All IP blocks are synchronized with the 104 MHz clock. The processor system reset block provides a unified reset for all IPs. The XADC samples analog signals and sends the data to DDR memory via AXI DMA. The ARM cores manage both XADC and DMA through AXI light interfaces. Don't forget to validate the design to generate all required AXI address mappings. Add the top HDL wrapper, and then you can proceed to synthesis the design. After synthesis completed, open the synthesized design and navigate to the I/O ports window. Assign the VP and VN ports to the correct FPGA pins based on the selected evaluation board schematic. Now you can generate the bitstream. Finally, export the hardware as an XSA file to be used in Vitis for application development. Connection to analog discovery with loopback. We will use the analog discovery to generate different DC and waveform signals and feed them into the FPGA board. To validate the generated signals, we can create a loopback to the analog discovery oscilloscope input. This figure shows the locations of VP and VN on the PYNQ Z2 board. For proper connection, the positive signal should be connected to VP and negative or ground signal should be connected to VN pin. The XADC operates only with input signals in the 0 to 1 volt range, so we need to apply an offset to sine waves or other signals accordingly. To meet this requirement, We can generate a cosine wave with an amplitude of 0.5 volt and apply a 0.5 volt DC offset to shift it into the 0 to 1 volt range. In Vitis, we first need to create a new stand-alone project using generated XSA from Vivado. Select Hello World template from the listed project. Download the provided C code from GitHub and replace the content of Hello World file with the provided code. Then proceed and build your application. Now, let's run the Vitis application and validate the XADC design. The application captures the input analog signal and print the first 100 values. Since visualizing data in Vitis is challenging, we will initially apply different DC voltage levels between 0 and 1 volt. However, if you prefer, you can also apply different waves. As you can see in the terminal window, the printed values perfectly match the applied voltages from the analog discovery. We can conclude that XADC has a good resolution for DC voltage and performed a great job to measure the DC voltages. Pynq Application. On the Pynq, we can easily observe signals, so I'm going to experiment with different waveforms and different frequencies. Let's start with a cosine wave. The XADC captures the cosine wave accurately, and we can also test different frequencies, ranging from 5 kHz to 200 kHz. As we increase the frequency, the amplitude of captured signal decreases. It shows that the XADC circuit is filtering the higher frequencies. To be able to see the signals clearly, I comment the y-axis limit in the code. Then the figure will adjust itself to the new amplitude of captured signal. Next, let's try a pulse signal, which has rapid transitions. As shown here, the PYNQ Z2 board struggles to capture signals with fast variation, and the rising and falling edges of the pulse waveform appear filtered. This may be due to the capacitor between Vp and Vn, which acts as a low-pass filter and attenuating fast changes in the input signal. However, the analog discovery oscilloscope captures the pulse signal without any issues. Unfortunately, when testing other waveforms, such as sawtooth or triangular signals, the XADC also fails to capture them accurately, as their rapid transitions are filtered out. Again, here the analog discovery oscilloscope samples the signals perfectly. That shows the input signal has a good quality.